Hello all, today we discuss about design of synchronous sequential logic circuit. So first of all, we know that the combinational circuit has no feedback, but in a sequential circuit there is a presence of feedback, and we have learned that the sequential circuit employs combinational circuit as one part and a few flip-flops as the other. The flip-flops are used as a memory device where we can store binary information bitwise in each flip-flop. The input of each flip-flop is the output of the combinational circuit, and the output of the flip-flop are again feedback to the combinational circuit as a secondary input. The primary input is known as x1, x2, xn are the external input, and the output of the flip-flop taken together is called the present state of the circuit, or simply called the state of the circuit. The state of the circuit changes to a new one when the flip-flops are triggered with a clock. This change will depend on the input of the flip-flops which are ready before the triggering. This new state in which the circuit will enter after the application of the clock is called the next state. So first state is called the present state, and if we changes the input and apply the clock trigger, then it is called the next state. So the next state is coming. So now next state is the present state, and the inputs of the flip-flop for which the transition from present state to the next state occurs is called the excitation input of the flip-flop. And for synthesis of the sequential circuit, the state table and the state graph are the best design tools for the approach. Now what is a state table? So state table, or it is also known as, another is known as state graphs. So these two are very important. One is state table and state graph, from which we can design our sequential logic from one state to another state. This table has three parts as described. First one is that the first part of the table indicates the present state of the circuit. This indicates the output of the flip-flop before application of a clock. These states may be described either by using binary 1 and 0 of the Q output of the flip-flop, or by using alphabetically symbol like a states S0, S1 up to Sn respectively. Number point 2. Second part is a table indicates the change of the present state to the next, influenced of external input or input when the clock is applied. Okay, so these are state from present state to the next state transition. This is also the part of the state table. And third part is more important. The third part of the table indicates the output of the circuit. There are basically two different types of circuitry. One is Mealy type and another is Mood type. For Mealy MEELY, for Mealy type circuit, the output depends on the external input. Student, please note down. For a Mealy type circuit, the output depends on the external input. So the number of column in this part will be equal to the number of possible variation of the input. And for the Mood type, the outputs are the function of the present state only. So the number of columns depends on the number of output. So therefore we show the table, two tables. Okay, just a minute to show the tables. Okay, right now here we mention this is the present state 1. Here we present our next state. Okay, and these are the outputs Z1 and Z2. Okay, and the states are S0, S1, S2 and S3. There are 4 states, and for input x equal to 0 and x equal to 1, these x are external input. Like consider these are the states for x equal to 0 from S0 to S0. So there is no change. I'll discuss in a graphical model also. Is S1, and for x equal to 0, x equal to 1, this is 1 0, this is 0 1. Just consider if we design the sequential circuit by this way, so our design approach depend on this table 0 0 and 1 1. So this is a state table for Mealy type circuit. So what we known as the Mealy type circuit, the output is depend on the external input. So the number of columns in this part will be the equal to the number of possible variation of the input. So here we see that the possible variation of input equal to x equal to 0 1, x equal to 1, x equal to 1. So the possible variation is that x equal to for 0 there is one output, and x equal to 1 there is output. So this is a Mealy type circuit. And for Mood type circuit, next one is present state. This is a present state. Okay, this is a next state ns. This is for x equal to 0 and x equal to 1 also, and this is our output. Okay, the two output equal to z1 and z2. Now consider the present states are s1, s2 and s3, and for say this is s1, s2, s3 and s0, and this is for s3, s1, s2 and s1, and the outputs are presented in this form. For Mood type circuit, the output of the function of the present state only. So the number of the columns depends on the number of output. So here number of columns depend on the number of outputs. Here z1 z2 are the two outputs, and x is the external input. And so from this table for Mealy type circuit, the structure for its states table can be reduced by writing the output z1 z2 along with the next state table. Okay, in the next state table we convert this table in a reduced manner. So how the reduction is possible? So this is the first of all, this is the present state. Okay, this is our next state, and here two conditions are met. One is for x equal to 0, x equal to 1. The present state array is 0, s1, s2 and s3. Now look in this table. So for x equal to 0, so what is our transition from s0? For x equal to 0, s1 to then s1, for x equal to s3. So just copy this. This is s2, this is s2, this is s3, this is s1. But what are the outputs? Just we represent in a, this is dash. For x equal to 0, the output is 1 0. This is okay. The output is 1 0. And next is 0 1. Okay. Next is yes right. Then 0 1. Okay. Next 0 1. This is 0. So this is 0 1 also. This is 0 0. Yes right. This is 1 1. Okay, though. So this is basically the reduced table approach, and this is also shown by the graph, another graph which is known as the state graph or this state transition graph. There are 4 states, and see that when by this external input excitation, when x equal to 0, then s0, the transition is s0 to s0. So here this is in a loop, and we here noted x equal to 0, and the output is 1 0. Yes right. And now when x equal to 1, this transition goes from here to here. This for x equal to 0, and the output is yes right 0 1. Okay, and that's why from s1 this is also one loop here for x equal to 0, and the output is 0 1. And when this is 1, this is transition to this x equal to 1. Sorry, this is x equal to 1. I'm sorry, this is 0 1. Okay, and now same for this s2 for this s2. What is the transition for x equal to 0? s3. What is the output? This, and again these are valid for both cases, because in the both cases the transition is s3. Now when s3, what is the transition for x equal to 0? s0. Okay, now this is for x equal to 0, and what is the output? 0 1. And when this is 1, this is s1 means from here to here. This is for x equal to 1, and what is the output? Is 1 1. So this is the state diagram table or state transition table of the synchronous sequential circuit, and this table helps us to design a synchronous sequential circuit. Okay, now we represent another example. So the problem is that draw the state graph for the following state tables. Okay, the states table look like that. So first of all, this is the present state, and this is the next state, and here two inputs are external input named as x1 x2 when this is 0 0, and next one x1 is equal to 0 1, and next one x1 x2 equal to 1 0. So the states are S0, S1, S2 and S3. These are the states, present states, and this is S0, S1, S2, S0, and the corresponding output are 0 1 0 1. So this is basically a, yes, right, this is a mode type sequential circuit, and this is S1, S3, S2, S3. So this is for outputs are this, and this is 3, S0, S0, S2, and the outputs are 0 1 1, yes, right, 0. So the state transition graph, first of all we draw the 4 states. Okay, look like that. Now see that when x equal to 0 0, the output is 0 is from S0. So this is for input 0 0 and output equal to 0. When this is x1 x2 equal to 0 1, then this is transition to s1. So this is for 0 1 and the output is 1. When x1 x2 equal to 1 0, then this is goes to s3. So this is for 1 0 and the output is 0. So this is the first transition from S0. Now from S1. From S1, this is a loop, because for x equal to 0 0 and the output equal to 1, then this is goes to x3 for 0 1 and the output equal to 0, and then it goes to S0 for 1 0 and the output equal to 1. Next for S2. For S2, this one loop is created here, because this is for 0 0, the output equal to 0. Now S2, now again here you draw that this is the same approach. This is also for S2. So this is for 0 1 and the output equal to 0, and for this is S0. Now from here to here, this is the condition of 1 0 and the output is equal to 1. Okay. Now for S3, first transition is for 0 0, and this is 1 from S3, and this is, they are also loop here for 0 1, this is 1, and from here to here this is 1 0. This is a state diagram of the state graph from the following table. Okay, this is very easy to draw the state graph from the state table.